예, 그러면 오늘 문제 해설 그리고 이제 수상자 발표 시작하도록 하겠습니다. 오늘 순서는 문제 3번에 해설부터 시작을 하도록 할 거고요. 우선 지난 한 달 동안 이제 챌린지 문제를 푸시느라 수고 많으셨고, 저희가 이제 그 채점을 다 끝내고 이제 수상자 발표도 해설이 끝난 뒤에 진행을 하려고 합니다. 우선 1번 문제와 2번 문제 해설에 관련해서는 이미 유튜브 채널에 올라와 있고요. 만약 그 문제에 대한 질문이 있으신 분들은 오늘은 이제 3번 문제 해설, 그 3번 문제를 담당하신 윌리 박사님께서 발표를 해주실 거기 때문에 그 해당 문제에 질문 있으신 분들은 이메일로 저희한테 연락을 주시면 감사드리겠고요. 오늘은 이제 챌린지의 마지막 문제, 3번 문제인 이제 트로트라이제이션 문제에 대해서 윌리 박사님께서 설명해 주시도록 하겠습니다. 문제 해설이 끝난 뒤에 저희 행사 이제 최종 그 우승자 발표도 이어서 있도록 하겠습니다. 시작하기 전에 저희 이제 동시 통역을 진행을 할 계획입니다. 그래서 수신 언어에서 한국어를 설정하시면은 동시 통역된 언어로 들으실 수 있으니까 이 부분 참조해 주시면 감사드리겠습니다. So Willie, you can start your presentation about the problem number 3.
Excellent. Thank you, Junki.
좋습니다. 감사합니다. 김 교수님 소개 감사합니다. 시작하도록 하겠습니다. 여러분 환영합니다. 제 이름은 윌리고요.
At IonQ, and it was very fun to develop this problem for you guys. I hope you enjoyed it. I think it's quite an interesting problem for many reasons, so we'll talk about that in a second. But I really hope that it was a cool experience for you guys. So let me start by introducing this challenge. So this is a trotterization challenge. This means that we want to use a quantum computer to simulate quantum time dynamics. I think it's a very cool problem for a number of reasons. One of them being the fact that this is basically why we started thinking about quantum computers in the first place. So if you go back to the great physicist Richard Feynman and what he was thinking about in the 80s, right? People were trying to run molecular dynamics simulations. They were trying to understand nature and how matter evolves over time at a molecular or a single atom level. And they found it to be quite a difficult problem because the computation that's required in order to run these simulations is tremendous, right? And especially back then, almost I guess more than 40 years ago now, they didn't have the computers that we have today. But even with the computers that we have today, as we'll see in a bit later, it's quite a difficult challenge to even try to get more than a few hundred molecules, or even 100 atoms or something like that. You're going to run into trouble fairly quickly. So one of the, I guess, an idea that was put out by Feynman is that why are we even trying to simulate nature, which is governed by laws of quantum mechanics, using a machine that is governed by a totally different set of laws, namely the laws of classical physics, right? Wouldn't it make sense to construct a machine that is ruled by the same laws of physics as nature, right? And that's a quantum computer, right? We want to somehow leverage the capabilities of, or the physical phenomena that are only allowed within the world of quantum mechanics in order to simulate quantum mechanical systems. So that's one of the reasons I find this problem quite interesting. It gets really to the core of why we started thinking about quantum computers in the first place. Now, that being said, we're pretty far along the way, and the way that we think about these computers today is very different than what Feynman had in mind. I mean, I have no idea, but it's probably fairly different. And I mean, at least we have the computers, right? The quantum computers exist today, and we can use them, right? What's even cooler is that we can leverage modern computing frameworks, right? We can use modern clouds. We can use all of these very sophisticated tools that we've been developing over the last few decades in order to use our quantum computers, right? So we can basically the way that we do it today is we leverage fairly sophisticated cloud computing protocols. We have very well-developed programming languages, and we use all of this technology stack in order to control these new machines, right? But okay, I guess the caveat is, okay, they're quantum computers of today, they're pretty amazing things, right? But the issue, or let me say, it's not an issue, but I guess one of the things that you need to consider when you're using these machines today is that they're not perfect yet, right? So what that means is that we are living in something that is called the near intermediate scale quantum era, or NISQ era. And what this means is that we have devices, they exist, you can use them. They are of intermediate size, right? And roughly that means that you have a few dozen qubits and you can perform a few hundred operations on them before you start hitting the boundaries of, or the frontiers of what is possible today. And that's largely due to the, or the key piece there to consider is the noise, right? So why, why we want to think about noise, or what is noise? Well, we were talking about these quantum computers as being built out of, or trying to leverage the phenomena that can only occur within the laws of quantum physics. Well, these phenomena, they only apply to very tiny systems, right? You need to think at the individual molecule or individual atom level, right? Something like that. So basically, you want to somehow isolate tiny pieces of matter, but also be able to manipulate and control them at the same time. So that's a bit of a dichotomy. But in any case, what that means for us today is that because these aren't perfect just yet, or in this era, every operation that we perform on a quantum computer introduces some noise, right? So we start to deviate from the calculation that we want to perform with each new gate in the circuit, with each rotation of a qubit, etc. Right? So we need to be clever. We need to come up with ways of reducing the number of operations. We need to come up with more efficient algorithms, right? We need to do some algorithmic development in order to solve relevant problems today or in the near future, right? And this problem gets to the heart of that matter for the quantum time dynamic simulation problem, right? So your typical trotterization scheme will result in fairly deep circuits. And the whole point of this challenge is to try to reduce the number of operations that are required in order to perform the same quality simulation. Now, the way we go about that, very coincidentally, and one of the other reasons I find this problem fascinating is because the compression scheme, the way of finding an equivalent circuit that is much shorter, involves many less operations, but can still perform at the same quality. This compression scheme is powered by something that's known as the Yang-Baxter equation. So we'll talk about it a bit later on in the guise of a symmetry or reflection identity. But this equation appears in many seemingly unrelated areas of modern math and theoretical physics. So I find that quite fascinating. In fact, before I was working at IonQ, I was doing a lot of research into topological quantum computing, which is based on things called anyons, the Yang-Baxter equation features prominently describing that kind of physics. It also comes up in things known as quantum groups, solvable lattice models. Anyways, I don't want to keep going in that direction, but it's quite a neat mathematical tool. I'll just say that. As you saw later on, it's also connected to things like the braid group, from which come things like knot invariance and other very interesting features. So, anyways, this problem is quite nice. So, let me talk a little about how this was set up, or at least the I guess the object of this problem. So, as you go through this, this is broken down into a few parts. So the first thing that we need to understand are the quantum time dynamics. So how do quantum systems actually evolve? In this problem, we're simulating the time dynamics of something that's known as a spin chain. We're focusing on a one-dimensional chain with only nearest neighbor interactions. And that chain is going to be governed, or its dynamics are going to be governed by the Schrodinger equation, which is this time-dependent partial differential equation. And turns out that this equation can be solved by something that mathematicians would call matrix exponential, and physicists would know as the time propagator, right? So basically what we want to do is approximate or implement this time propagator, and we'll want to leverage the quantum computer for that, just because it would be extremely expensive to try to do it on a classical device, right? And not exaggerating here, but you could get into very prohibitive scales very quickly, right? So as this example illustrates, I mean, even if you had just 20 sites and you consider, say, a very naive algorithm for trying to approximate or compute this matrix exponential or this time propagator on a classical device, you would need something like 10 to the 20 flops, right? That's quite a bit. The largest computers that we have today function on the exascale, which means that they can do 10 to the 18 flops. So, maybe you could do 20 sites on a problem on the largest supercomputer on the planet. And that would take you something on the order of something like a few minutes. But, that's only 20 spins, right? And in nature, we want to consider much larger and complex systems. So anyways, that's some motivation for why you would want to do this on a quantum computer. And then, of course, the real challenge of this problem will be to try to do it on a quantum computer today, right? Which means that we need to implement this time propagator in a clever way so that we can avoid running into these very deep circuits. Okay, so it all starts off by thinking about just the two-particle case. So what happens if you have just a spin chain with two pieces? The way that we're going to do this basically maps one or assigns one qubit in your quantum circuit, in your quantum computer, to a spin. So there's a one-to-one mapping between these two-level quantum systems. So we'll just start off easy and think about this small case. Your first task here was to implement these time propagators for this small two-particle or two-spin case, right? And what's neat here is that you can implement these propagators using just a handful of gates, right? Now, when we talk about complexity on the quantum computer, the most expensive steps are the entangling two-qubit gates, or the C0 gates. So that's what we want to focus on. So we typically want to focus our attention on counting the number of C0 gates in the circuit. And what you see here, what's neat about this, these particular time propagators, is that you would need at most 3 C0 gates for each block, right? Each propagator on 2 qubits. basically I'm decomposing this problem where we'll have a bunch of spins into, first we'll want to think about just the 2-spin case, then we'll extend to 3 spins, and we'll think about how the different time propagators on the different spins interact with each other. What are the relationships amongst them? And finally, we'll extend to higher, or larger systems. So anyways, that was the first task here, is to implement these gates, and you could check your result, right? This was the expected result. So hopefully, I think most everyone got through this part. Anyways, the next bit is really introduces the complexity of this problem. So the issue, let's say one of the biggest issues in addressing this problem is, or results from the fact that matrices, they don't commute with each other in general, right? So the issue is that we cannot directly factor, or at least we haven't found a way to directly factor our time propagator as a product of, the general time propagator as a product of time propagators for smaller blocks or for 2-qubit pieces. So, we won't be able to do this directly, but we might be able to approximate it. And this explains why we end up with deeper circuits. So a common way to do this approximation is by using what's known as the Trotter-Suzuki formula. The Trotter-Suzuki formula is based on this calculation, that you can express the limit of this exponential, where you've added a bunch of different Hamiltonians, as an alternating product, or as a limit of an alternating product in the limit of infinitely many layers. Basically, the approximation scheme will just truncate this infinite alternating product. We'll just take a finite number of layers, and we'll call that a day. So this is the part where things start to get interesting, right? We start to identify commuting families of operators or time propagators, small pieces of the whole thing that we need to compute. And we realize that we can come up with the first step is realizing that you have, or that this large commuting family allows you to set up your circuit so that it has just alternating layers, right? 2 big pieces that alternate, one and the other. And that itself saves you some circuit depth, right? But now the whole challenge here will be to try to get rid of that factor, that number of layers factor that we need in order to increase the approximation quality. So the goal of this scheme is to come up with very high quality approximations that always have the same depth of the circuit. So that's our goal. That's where we're going. Anyways, the implementation challenge here was to set up your circuit so that you lay down these blocks in a brickwork fashion. And you're leveraging the gates that you've previously implemented. So now, why are we doing this, or what's the proof of concept here? Well, we're going to use this to measure a physical property of the system. And this will allow us to judge whether or not it'll be one way. But an interesting application, right, of this calculation, it'll allow us to compute a physical property of the spin chain. In this case, we're going to measure the staggered magnetization, which is essentially how coordinated the spins are, if you will. So we'll approximate this as a function of time. And basically, this quantity, this alternating sum, is bounded between -1 and 1, and we want to see how it evolves over time. Right? What we'll see is that if we approximate this quantity using the very deep circuits, we'll, on a real quantum device, we'll quickly lose approximation accuracy. And actually, it won't be able to decide whether or not the magnetization is close to 1 or -1, right? So I'll see in a second, I'll pull up a solution plot, and we'll see that actually very quickly, the staggered magnetization just somehow converges to 0. But the issue is that that's just the noise in the quantum computer because you're feeding it such a large or such a deep circuit. So anyways, in a second, once we look at the solution, we'll see the effect of the compression scheme and how actually using this compression scheme, being clever about how we're doing the calculations on the quantum computer, allows you to compute physical properties more accurately, right? And that's what really we want to do. So anyway, the challenge here was to just implement the staggered magnetization operator. And the way to do that, as you showed in this exercise here, in this theory exercise, was by doing a weighted sum of the energies or the eigenvalues of your Hamiltonian. So basically, one part was, or essentially all you had to do here is tell me what are the energies, what are the possible observable values of this staggered magnetization for each possible state of the spin chain, each observed or measured state, right? Okay, so then in the last stage, this is where things start to get interesting. This is where we pull in the Yang-Baxter equation to help us with the compression scheme. And again, the reason we want to do this compression scheme is so that we can avoid running very deep circuits on noisy devices. So here's your parametric Yang-Baxter equation. It is a relationship between block or time propagation operators on different qubits. Symbolically or pictorially, it looks something like this. So it basically gives you a way to replace the arrangement of different blocks, right? So whenever you have a chain of 3 blocks, you can somehow flip the order. This we'll call the reflection symmetry, in keeping with this paper by Peng et al. But you could come up with other names if you wish. The other part of this, or the thing that really explains the compression scheme, is that you need to realize that doing time propagation on the same site twice, right, or doing it consecutively, is the same as just applying the same or one single time propagation operator for a longer time, right? So this is called the merge identity. Essentially, it'll allow us to collapse some blocks and just remove them from the circuit. All you have to do is update the parameters in your time propagation blocks, right? So if you think about it that way, basically the compression scheme is just a way of rearranging the blocks in your circuit and deleting some of those blocks just because you realize that doing 2 consecutive time propagation operations on the same site is the same thing as just doing a single time propagation operation for a longer time, right? For a different parameter value, if you will. So that is the goal of this exercise, right? And again, it's as in the previous stages, this will be broken down into a few different tasks. The first one is to implement this single Yang-Baxter move or reflection symmetry. So what you should do here is, or your task would be to input values for the parameters for each of these 3 blocks, and then come up with a function that spits out parameters for the new arrangement of blocks, right? So you can think of this very programmatically as just a function that takes in some parameter values and then returns some other parameter values, some updated parameter values for the circuit layout, right? And once you have that, then you can use that Yang-Baxter move in order to produce this mirror reflection using a sequence of moves, right? So here's how it works for 4 qubits. So if you have an arrangement of 6 blocks on 4 qubits, basically you want to single out certain sequences of 3 blocks and do this one step at a time. All right. So for example, to go from step 1 to step 2, what you want to do is apply a Yang-Baxter move on this block, this middle block, and this other top block, right? So this this arrangement of 3 blocks becomes this arrangement, and then so on and so forth. So the hint here is, or the way to go about this is to simply number your blocks. So say this is block 0, block 1, 2, 3, 4, 5. And to keep track of the different vectors or sets of parameters for each block as you apply each of these Yang-Baxter moves, right? So anyways, once you have that mirror symmetry implemented, basically you can use it to compress circuits on 4 sites. And now, if you really want a challenge, then you could come up with a similar move in order to compress circuits on larger than 4 sites, right? So that's a real challenge. And I'm very proud to announce that one group did take a stab at this, and they came up with a nice layout for a possible algorithm that could be used in order to implement that compression scheme. So kudos to you guys. That was a great job. Let me now show the results, and for the last bit, I'll come back to this screen to talk about this algebraic formulation, because there's some very nice mathematics under the hood here that basically tell you how far you can compress down your circuit, or what's the limit, what's the depth for which any circuit compression scheme would have to have, right? So let me switch my screen to talk about these results, and then we'll come back to the algebraic formulation for just a second, because that is certainly a more advanced feature of this. Okay, so here are the results of our scheme. Some of you saw a plot that looks like this in your results. So again, kudos to you if you obtain something similar to this. But this is the goal of this scheme, right? This is why we want that scheme in the first place. So let me explain the different curves here. First we have the ideal. We have 2 kinds of simulations, or we're running this on 2 different kinds of backends. One is an ideal backend. This means that this is a classical computer simulating a quantum one with no noise or no errors as you apply the gates. And then we have our noisy IonQ, well, we have our IonQ Harmony QPU, which, as a feature of quantum computing being a nascent field, is noisy, right? Introduces some noise per gate. And we can see the differences between the deep circuits that we run on the ideal hardware. That's the blue one, deep circuit ideal hardware, blue one, and the orange curve, which is the deep circuit that is being run on the quantum hardware. You can see there's a tremendous difference, right? The curves look nothing alike. And as I said, the the magnetization prediction from the deep circuit is actually converging to 0, right? So it's not telling us anything about that physical system. It's not being able to compute the physical properties just because you're dealing with a very deep circuit and all the noise in the hardware. However, once you compress your circuit, you get much better results. So the green dots show that the compressed circuit, if you run it ideally, indeed matches the uncompressed version exactly. And in the red one, which is run on the noisy hardware, you run the shallow circuit on the noisy hardware, that shows much better fidelity. It's predicting that physical property, magnetization as a function of time, with a much higher fidelity. So this is the result for 3 qubits, and I'll just briefly show the result for 4 qubits here. You get very similar results. Again, the noisy hardware can't deal with those deep circuits. But if you compress the circuits, first of all, you're getting an equivalent computation, right? That's the almost perfect fidelity between the green and the blue curves. And then you have this red curve, which is the compressed circuit being run on the noisy hardware. And you see the fidelities, it's not exact. There is still some noise, but it's much, much, much better than the uncompressed version. So this was the goal of the exercise, to illustrate that indeed it is possible to sometimes, or for some problems, it's possible to be a bit more clever about how we're going about these computations on the quantum device. We can make a lot of algorithmic improvements, and they pay off, right? They pay off. So you can use this compressed circuit to say something about the underlying physics, whereas you couldn't do anything with a directly trotterized circuit. Now, there's a bunch of extensions to this work, of course, one of them being, how do we implement this compression scheme for larger for larger circuits, more sites, right? Other things you can do is you can look at higher order Trotter-Suzuki formulas to get better approximations much faster. You could also look into better approximation for the parameters. So for this challenge, you were provided a function that gets optimized parameters for the time propagations, and you could use that as a black box as you implemented your method. But that's just based on a least squares computation, right? It's based on some numerical minimization. There are much better and more performant tools in order to find those parameters, right? So you could come up with a more numerically stable algorithm for that. Some folks in the literature cite methods that rely on something called Givens rotations and certain orthogonal decompositions. So anyways, there's a lot of follow-up work. So if you enjoyed this kind of problem, I'm definitely happy to get in touch and talk about how to think about extensions, right? For the last bit, let me just talk about another direction in which you could take this problem, and that's deeper into algebra. So the reason this works from a mathematical standpoint is actually related to the braid group, which is in fact related to the symmetric group, right? So the reason this works is or the way to explain the number of blocks in the compressed circuit and how many blocks any compression scheme like this would require, it actually comes down to knowing something about the symmetric group, right? And that's just the group of permutations on n letters. So that I think is quite interesting. The link is built, or the bridge that connects these two things is something that's called the Hecke algebra. So the reason these two structures are connected is because our block operators, so if you forget the parameters in our Yang-Baxter equation here, if we forget the parameters, we're actually just looking at the braid relations. Right? The braid relations are down here. And these are the relations that generate the symmetric group, right? So if we think about the symmetric group being generated by transpositions, which means that you just switch neighboring objects or adjacent objects, then you know, those generators will satisfy these braid relations, and basically, you know, this whole or I mean, like this, basically the block operators give you a representation of this gadget here, the Hecke algebra. And like I said, the reason you need at most n choose 2 blocks in your, or sorry, yeah, the reason you need these n choose 2 blocks and exactly n choose 2 blocks in your compression scheme is because the longest permutation on n objects has a decomposition in terms of this many transpositions, right? You need n choose 2 to express the permutation that reverses everything, the reversal or inversion permutation, right? And they're somehow connected to that. So a couple of folks took a stab at this part, this algebraic formulation, this argument. So again, kudos to that on progress in that direction. Again, now that I've talked about it, maybe you'll want to go back and think about this some more. I'll just say that the hint is that you know, this is somehow related to the symmetric group and permutations. So I hope you find that quite interesting. Like I said, there's a lot of extensions, many directions in which we could take this problem, but you know, for now, this is it. So kudos to all the participants. You guys did great work, and I was very excited to review your results, and you know, very proud of those who made it till the very end. So great job, everyone. Thanks for participating. So off to you, Junki. I think are we ready to present the winners?
Yes. So thank you for your nice lecture about the problem number 3. Before we move on to the winner announcement, we can hear some like questions from the audience if we have some.
Oh, absolutely. Thank you. I forgot about that.
혹시 질문 있으시면은 편하게 해주시면 되고요. 네, 질문 한국어로 하셔도 되고 채팅창에 남겨주셔도 됩니다. 잠깐 기다려보겠습니다.
Thank you.
네, 그러면은 질문이 없으므로 다음으로 넘어가도록 하겠습니다. 그러면은 이제 마지막으로 이제 이번 행사의 우승자를 발표를 할 건데요. 저희가 이제 총 36분이 참여를 해주셔서 굉장히 많은 분들이 참여를 해주셨고요. 그중에서 이제 우승자는 그 학부생 중에 1분, 그리고 대학원생 중에 1분, 그래서 가장 우수한 성적을 받으신 분들께 우승자 2분에게 장관상을 수여를 하게 되었습니다. 그리고 장관상 이외에도 참여하신 모든 분들께 문제를 푸신 정도에 따라서 저희가 이제 기프티콘 등을 보내드릴 계획인데요. 이 부분은 개별적으로 안내를 드릴 것이니 참고 부탁드리고요. 그러면 오늘 여기에서는 최종 가장 높은 점수를 받으신 장관상을 수상하실 2분을 이제 발표를 해드리도록 하겠습니다. 정식 수상은 저희 센터로 초청을 해서 2분을 장관상 수여를 할 거고요. 오늘은 우승자만 발표를 하도록 하겠습니다. 그래서 우승자는 2분, 말씀드린 대로 이제 학부생 1분, 대학원생 1분이고요. 학부생 부분에서는 정재원 학생, 서울대학교의 정재원님께서 수상을 하셨고, 그리고 대학원생 부분에서는 카이스트 한국과학기술원의 김형규 님이 수상을 하시게 되었습니다. 두 분 모두 축하드립니다. 여기 한 분 또 계시네요. 예, 축하드립니다. 예, 그 외에 이제 기프티콘은 저희가 개별적으로 안내를 드리도록 하겠고요. 긴 시간 동안 이 챌린지 문제에 참여하시느라 고생 많으셨고, 이번 행사를 통해서 또 많이 양자 컴퓨터에 대해서 배우는 기회가 되셨길 바랍니다. 그러면 저희는 오늘 그 렉처 그리고 우승자 발표를 여기서 마감을 할 거고요. 여기 링크 채팅창에 올라와 있는 행사 그 해설에 대한 만족도 조사 링크를 한번 작성을 하시고 작성해 주시면 감사드리겠습니다. 예, 오늘 모두 수고하셨습니다. 감사합니다. Thank you all. Thank you. 예, 축하드립니다.